Okay, so let us look at micro pumps. Micro pumps are important component in a microfluidic system that are used to transport fluid in microfluidic devices in a controlled manner. Okay. So micro pumps can be divided mainly into two categories. One is mechanical pumps, where mechanical energy is added to the boundaries of a micro pump to generate increase the pressure of the fluid inside. So thus that transport the fluid inside the chamber gets transported. Okay. The second type in non-mechanical energy like electrical energy or magnetic energy is added to a the fluid present inside a micro pump, and in doing so the momentum of the fluid increases, and also the increase in the momentum results in increase in pressure. So that is how the fluid get transported inside microfluidic channel. Okay. So we look at micro pump. Okay. So micro pump are a component in microfluidic system for controlled transport of fluids. So micro pump can be categorized into mechanical micro pump and non mechanical. Okay. And the mechanical micro pump can be categorized into displacement pump and dynamic pump. Okay. Now let us first talk about displacement pump. So in displacement pump the energy is added periodically to moving boundaries containing fluids. Okay. So in displacement type of mechanical pumps the energy is added continuously to the boundary containing fluids, and as the energy is added the pressure of the fluid present inside the boundary increases. So that is how the liquid gets transported to another location. One example of displacement type pump would be piezoelectric driven valveless micro pump. Okay. So when energy added the pressure inside the chamber increases, so the fluid gets transported. Okay. And some of the examples of displacement pumps are piezoelectric pump and we have peristaltic pump. Okay. Now in case of dynamic pumps, in dynamic pumps the energy is added continuously. In displacement pump the energy is added periodically. In dynamic pump the energy is added continuously, thus increasing the pressure inside the chamber. Okay. So energy is added continuously to increase the velocity of the fluid present inside the chamber, and as the velocity increases the pressure also increases. Okay. So in dynamic pumps, energy added continuously, and so that continuous addition of energy gives rise to increase in velocity. Okay. So, and this higher velocity leads to increase in pressure. Okay. And one example of dynamic pump is the ultrasonic pump. Okay. Next, move on to non-mechanical pumps. Okay. So, in non-mechanical pumps, the energy, a non-mechanical energy in the form of electric field or magnetic field is added onto the fluid present inside a chamber, and due to addition of the momentum, the fluid velocity would increase and the pressure of the fluid will increase. Okay. So, momentum added to fluid by converting non-mechanical energy such as electrical or magnetic energy into kinetic energy. Okay. And the example could be electroosmotic micropump. Okay. Now, if we compare the non-mechanical type pumps with mechanical type pumps, mechanical type pumps normally offer higher flow rates, but they are relatively larger in size. Okay. And non-mechanical pumps are offering relatively smaller flow rate, but they are smaller and easily integrated with the microfluidic systems. So, if you do a comparison, then the mechanical pump are larger in size and offer higher flow rate, whereas the non-mechanical pumps would offer smaller flow rates and provide ease of integration. Okay. Now, let us look at what are the mechanical pumps and what are the non-mechanical pumps. So, here you see a pneumatic micropump. Okay. So, pneumatic micropump is the displacement type mechanical micropump. Okay. And another displacement type mechanical micropump is piezoelectric micropump. Okay. So, here you have the thermopneumatic micropump, which is non-mechanical type, because the energy source is comes from the thermal energy. Okay. And here in an electrostatic micropump, which is a non-mechanical micropump. Okay. So, if we do a categorization, so we do first mechanical micropump, okay. So, the mechanical micro pump would have the displacement type and dynamic. So, under displacement we have check valve micro pump, then we have peristaltic micro pump, then we have valveless micro pump, and we have rotary micro pumps. Okay. And in dynamic we have ultrasonic and centrifugal. Similarly, in non-mechanical micro pump we have electrohydrodynamic micro pump, ESD micro pumps, then we have electrokinetic micro pump, which we have already discussed, which works on the principle of electroosmosis, and we have magnetohydrodynamic micro pump, and we have capillary driven micro pump. So, we will look at each of these micro pumps in detail. Now, here if you look at the pneumatic micro pump, the way it is it works is so this is the chamber, and one side of the chamber is open to a pressure source, okay, and the other side we have the fluidic inlet and fluidic outlet through valves. Now, when the pressure here is less than the inlet pressure, okay, so the pressure here is in less than the inlet pressure, the fluid will come out into the chamber, okay, through this valve. So, the valve will open simultaneously and the fluid will come inside the chamber, and when the pressure will increase than the outlet pressure, and simultaneously this outlet valve will be opening and the inlet valve will be getting closed, the fluid will go to the outlet. So, that is the principle based on which pneumatic micro pumps work. Similarly, piezoelectric pumps will works in a similar manner, but here the actuation principle is based on piezoelectric mechanism, okay, rather than pressure driven membrane actuation, okay. And similarly, in the non mechanical, in thermopneumatic we would have heaters, and there will be a fluid present here, and when you supply a thermal pulse, then the fluid will evaporate and there will be nucleation and bubble growth. So, that would actuate, so depending on the heat pulse onto the heater, that will actuate the membrane. Similarly, the electrostatic micro pumps would exploit the electrostatic force between two parallel plates. So, here is one parallel plate and the second one is on the membrane to actuate the movement of this membrane with respect to the top parallel plate, okay. So, let us look at what are the ranges of the flow rates that the different micro pumps can offer, okay. So, if you draw a scale here, and let us say this is 10 to the power minus 3 and this is 10 to the power minus 2, 10 to the power minus 1, 10 to the power 0, then 10 to the power 1, 10 to the power 2, 10 to the power 3, okay. Let us say this axis is the flow rate, which is in milliliter per minute. Now, the pumps that can deliver less than 0.5 milliliter per minute, and the ones that can deliver higher than 0.5 milliliter per minute are categorized separately. So these are going to be mostly non mechanical pumps. So you have electrokinetic pump, electrohydrodynamic pump, magneto-hydrodynamic pump, and also you have this ultrasonic, which is a dynamic mechanical pump. So these pumps can offer flow rates less than 0.5 milliliter per minute, and on the higher side we would have check valve pump, we would have peristatic pump, and we will have valveless pump. Okay. So these are the different flow capacity of different micro pumps. Now let us look at the actuation principle of this micro pump. Okay. So the actuators can be divided into two categories: external actuators, internal actuators. The external actuator based micro pumps are relatively larger in size because the actuation principle is outside the micro pump, whereas the internal actuator based micro pumps, the actuation principle, the mechanism is actually integrated with the micro pump. Okay. So actuators are external actuators and internal actuators, and these are they have large structure size, and they require large force for actuation and offer large displacement. Okay. Whereas internal actuators are easily integrated. Okay. So integrated with micro pump. Okay. Now the examples of external actuators are what we have seen earlier is the pressure based actuation, or we have the piezoelectric or electromagnetic. So these are outside the micro pump. Okay. Internal actuators are electrostatic. So these are actually inside the micro pump itself, electrostatic. Then we have thermopneumatic, where we can integrate heaters inside the pump chamber, thermopneumatic, and we would have thermomechanical. So it should work on the principle of the difference in the thermal expansion coefficient, thermomechanical micro pump. Okay. And these have distinctive advantages. Electrostatic, for example, will have will require lower power for operation. Okay. And they have very good response, they have fast response, and however the force that they exert are relatively small, and they are also reliable. So these are the characteristic of electrostatic based actuation. Similarly, thermopneumatic have large stroke. Okay. So the displacement volume is large, and the force that they can exert is also large, and thermomechanical will use large thermal energy, because we are talking about the expansion of the pump part of the pump material. So it will use large thermal energy. Okay. Now let us look at the mechanics of the pump membrane. Pump membrane is an important part of mechanical micro pumps. So let us look at the pump membrane mechanics. So, the pump membranes are normally are flexible and reciprocating in nature. These are flexible reciprocating membranes, and here if you consider a circular membrane, clamped around its edges and it is subjected to a pressure load, okay. So, this is the situation we would have, okay. So, we would have the pump membrane which is clamped around the perimeter, and this would be the maximum deflection y0, and at any r, let us call this is the deflection at yr, where this is going to be the r, and the capital R is going to be the radius of the membrane, okay, r, right. So, in that case we can write the deflection at r as the maximum deflection into 1 minus r square divided by r square whole square, okay. So, that is how the deflection of the membrane will vary along the radial direction, okay, where y0 is the maximum deflection, r is the membrane radius, okay. We can also establish the relation between the pressure. So, this is the pressure that is acting on the membrane for the deflection. So, we can establish relation between the pressure and the maximum deflection. So, relation between pressure and y0 has been estimated as P. So, this has been also analytically derived. So, this is going to be 36 T, T is the membrane thickness into central deflection y0 divided by 3 r to the power 4, okay, into E is the Young's modulus of the membrane material minus 1 minus nu square, nu is the Poisson's ratio, and into T square plus 16 by 35 into y0 square. So, this is how we can relate the pressure that is acting inside the membrane to the maximum thickness of the membrane, okay. So, all these parameters are known which you use for a membrane. Now, for dynamic case, we can determine the resonant frequency. So, the resonant frequency can be expressed as, so Fkn is going to be 2 pi beta kn square into d over m. So, Fkn is the resonant frequency, beta kn is the eigenvalues. So, these are the eigenvalues, and d is the flexural rigidity, okay, and m is the mass of the membrane. So, m is the mass of the membrane. So, the flexural rigidity d can be written as Young's modulus into thickness to the power 3, 12 into 1 minus Poisson's ratio square. So, this is the expression for the flexural rigidity, and k, the subscript that we are talking about, k will vary as 0, 1, and n will vary as 1, 1, 2. Okay. So, these are the vibration modes, these are the vibration modes for the membrane. Okay. And so, considering the first 3 vibration modes, we can write the value for the eigenvalue, value of the eigenvalue. So, the eigen values for first 3 vibration modes can be written as, so beta 01 would be 1.015 pi over r, okay, and beta 11 would be 1.468 into pi over r, and beta 02 would be 2.007 into pi over r. So, these are the first 3 eigen values for the first 3 vibration modes. Okay. So, using these values for a particular configuration of a membrane, we can calculate what is going to be its resonant frequency, which is an important design parameter. Okay. So, now let us look at what are the pump parameters. So, the important parameters for the pump will be the pressure head, the flow rate, and the power consumed by the pump, and also we are looking at the efficiency, the energy efficiency of the pump. So, let us look at the pump parameters. The important parameters here are the pump head. So, the pump head will be the total head at the outlet minus the total head at the inlet. Okay. So, H, the total pump head will be P over rho plus U square by 2G plus Z, that is at the outlet of a pump, minus P over rho plus U square by 2G plus Z at the inlet of the pump. Okay. Now, if you say that the maximum pressure is P max and the maximum flow is Q max, you can write down the expression for the power consumed. So, okay, the power for the pump is P max into Q max. So, this is flow rate. So, there is a dot there, Q max divided by 2. Okay. And if you know the maximum head instead of pressure, then you can write rho G H max into Q max divided by 2. Okay. The other parameter that is important for the pump is the pump efficiency. So, the pump efficiency can be defined as, so eta, the pump efficiency is the power delivered by the pump, okay, which is P max Q max over 2 divided by the power, the energy, the rate of energy supply to the actuator. Right. So, in case of for example, a thermopneumatic based micro pump, the actuation comes from the thermopneumatic mechanism. So, based on the heater power that is consumed by the pump, and if you know the power delivered by the pump, you can find what is going to be the efficiency of the micro pump. So, now let us look at the simplest possible micropump, which is the check valve micropump. So typically we will have a chamber with an actuator on top, and on either side we would have two valves, one to control the incoming fluid and the other one to control the outgoing fluid. Okay. So the first pump that we look at is the check valve micropump, and so here you see an image of the check valve micropump. So this is the pump chamber, okay, and on top of the chamber you have an actuator. So this could be any actuator, it could be piezoelectric, it could be thermopneumatic, and that actuator is going to actuate the membrane, okay, so which is the boundary of the pump chamber. And on the inlet side you have an inlet valve, and on the outlet side you have the outlet valve, okay. So when the membrane expands, the liquid comes into the chamber through the inlet valve. So the inlet valve opens and the liquid comes to the chamber, and in the forward stroke when the membrane comes down, this valve is opening and this valve gets closed, okay. So we have a fluid gets transported from inlet to outlet, okay. So let us look at the important parameters to define this the check valve micropump, and one such parameter is the compression ratio. And compression ratio is defined as the stroke volume divided by the dead volume, okay. So compression ratio is divided as, so compression ratio is defined by psi, which is the stroke volume divided by the dead volume V0, okay. Now the second important criteria is the pressure that is required to actuate these micro valves, okay. So in the for the inlet valve, the pressure difference between the incoming supply and the pressure inside the chamber has to be greater than the critical value of the critical pressure that is required to open the inlet valve, okay. So the other important parameter is the pressure values across the valves, and here we should have P minus P in should be the mod of that should be greater than delta P critical. Similarly we need to have P minus P out has to be greater than the delta P critical. So the delta P critical is the critical pressure that is required to actuate the valve, to open or close the valve. So this is the critical pressure required to actuate the valve, okay, mainly opening, okay. Now for a gas pump we have an expression for the minimum compression ratio. For a gas pump, the minimum compression ratio has been estimated as, so minimum compression ratio for a gas pump is given by, so delta V to dead volume will be P0 divided by P0 minus delta P critical to the power 1 over K, K is the specific heat ratio minus 1, okay. So, this is the specific heat ratio and P0 is the ambient pressure, the atmospheric pressure. Just to give you an example, if you have a cantilever valve, so just as an example, we have a cantilever valve that has dimension 1700 into 1700 into 15 micron thickness. Okay. So, it is basically a cantilever plate that is getting actuated because of the inlet pressure. Okay. So, normally the valve will be, the cantilever will close the valve port, and when the pressure exceeds, then the valve port will be opening because of the deflection of the cantilever. So, if you have a cantilever which has 1700 into 15 micron dimension, and with the orifice where the fluid tries to get in is 400 into 400 micron, then typically the pressure, the delta P critical, it will be of the order of 10 to 100 millibar. So, that is the kind of pressure, actuation pressure we are talking about when you are talking about micropumps. Okay. Now, if you look at this equation, if you assume that we are talking about low pump frequency and the small critical pressure, then you can simplify the expression. Okay. So, for low pump frequency and small critical pressure, we can simplify the compression ratio of gas as 1 over K into delta P critical divided by P0. Okay. Now, for liquid we also have an expression for the compression ratio for liquids. The compression ratio is theta into delta P critical, okay, where theta is the compressibility of liquid. So, this is the compressibility of the liquid, and which is typically 0.5 into 10 to the power minus 8 meter square per Newton for water. Okay. Now, let us look at the design rules to make to design a check valve micropump. So, the design rules for check valve micropump. So, one important design rule would be the critical pressure that is required to open the valve has to be minimum, and that can be achieved by using a more flexural valve or materials having small Young's modulus. Okay. So, one important thing will be to minimize the critical pressure using more flexural valve design or using material with small Young's modulus. Okay. The second design objective has to be to increase the stroke volume, and to increase the stroke volume the requirement should be the membrane has to be of low stiffness. Okay. It should be more flexible. Okay. So, the second objective would be to maximize stroke volume. So, that is possible by flexible membrane. It is also possible by using large the actuators with large force, actuators with large force. Okay. So, the actuators, if they offer large force, the dead volume can be, the stroke volume can be increased. And the third objective has to be to minimize the dead volume. Okay. So, that we get the dead volume, the more liquid do not stay idle inside the chamber. Okay. So, would be to minimize dead volume, and this can be done using thinner wafers, using thinner wafers. So, the chamber depth has to be minimum. Okay. And the final objective has to be to maximize the pump pressure, maximize pump pressure, which can be achieved using actuators with large force. Okay. Now, let us continue our discussion with peristatic micropump. So, let us continue our discussion with peristaltic micropump. So, these peristatic micropump, they do not require any check valves, they do not require check valves, normally they do not require check valves, and their motion is based on the peristaltis motion that we use, how the food goes from our mouth to our stomach. So, based on peristaltis motion. Okay. So, if you look at the mechanism here, what happens is, so here in this particular case we have 3 different chambers with 3 different membranes actuated sequentially. So, this is the first step. What happens is this membrane is going up, okay, so that it creates a negative pressure. So, the liquid from the inlet comes inside, okay, and so in that stroke these 2 membranes, these are all controlled using a control system. The actuation of the membrane are automated. So, when this expands, these 2 membranes are going down. Okay. In the next stroke, so the liquid has already come in here, in the next stroke this membrane will go down, so the second membrane will go up. So, the liquid that has come in from the inlet will pass on to the second chamber, okay, and at the same time the third membrane is going down. So, the liquid cannot escape. Okay. In the third cycle, so this is the second cycle, in the third cycle the first membrane will go down and the second membrane, so the fluid is now present here, now this second membrane will go down and the first membrane is going down anyway. So, the fluid has only option to go to the third membrane. So, it will go into the third chamber, and again it will go back to the first cycle, and so when it goes back to the first cycle, the liquid present here, if that membrane will go down in the third cycle, so the liquid is going to exit, okay, and at the same time the liquid comes out here through the inlet because this chamber is moving up. So, these motion of the different membranes is occurring sequentially in a controlled manner to drive the fluid from the inlet to outlet using peristatic motion. Okay. One issue with the peristatic micropump is that when the micropump is operational, it is fine, the liquid will go from the inlet to the outlet, However, in situations where the micro pump is idle and you have already pumped some fluid from inlet to outlet to a high pressure source, if the micro pump is not operational, there is a possibility of backflow. Okay. Now, to prevent that, we would need one check valve upstream, one directional check valve upstream. Okay. So, one issue with check valve micro pump is that under non actuated state, so there is a possibility of backflow, there is a possibility of backflow. So, we need a one way valve upstream, okay, to prevent backflow. Okay. And some of the optimization strategy for the peristatic micro pump. So, optimization strategy we want to maximize the compression ratio, maximize the compression ratio. So, that gives us high flow rate. Okay. So, this together with the large stroke would give us the high flow rate, and we also need to increase the number of pump chambers. Okay. So, that would give you a high back pressure. Okay. Okay, so with that let us stop here.